So calculating enthalpy changes. So let's review a smidge. Standard enthalpy change for a reaction. That's delta H, 0, reaction. So this degree symbol, or 0, whatever you want to call it, that means it's standard. So the change in enthalpy, the standard change for a reaction. This is the enthalpy change for a process where all the reactants and products are in their standard states. So standard state definitions for a gas, the standard state is a pure gas at 1 atmosphere of pressure. For a liquid or a solid, it's the pure substance in its most stable form and the temperature of interest, which is usually 25 degrees. That's sort of like standard room temperature kind of thing, except here where you never know what temperature the room's going to be. And if you have a substance that's in solution, the standard state is a concentration of 1 mole per liter. So the standard entropy change for a reaction, delta S reaction with the, I'll call it a circle up there. So this is the entropy change for the process where we have everything in its standard state. Entropy is a state function, like enthalpy. It doesn't matter how you get there, it's just the difference is the same regardless. So we can say that the entropy, standard entropy change for the reaction is equal to the standard entropy of the products minus the standard entropy of the reactants. The entropy of the products in their standard states minus the entropy of the reactants in their standard states. So then we need to define these things. What are these? We're going to call them standard molar entropies. So enthalpy, we had to define where 0 was because there is no absolute 0 for enthalpy. We can't calculate that. And so we said we're going to call standard states of elements 0 and use that as a reference point. But for entropy, there is an absolute 0. And that brings us to the third law of thermodynamics. The entropy of a perfect crystal at absolute 0 is 0. So here is a perfect crystal, no defects. At 0 Kelvin, all movement stops. So these atoms are not even vibrating. They are literally frozen. They're completely still. Now, we haven't achieved 0 Kelvin yet, but it's theoretical, right? So, in theory, right? So if these are not moving at all, and there is only one way for them to be arranged, then W equals 1, right? Boltzmann's definition of entropy was a constant, his Boltzmann's constant times the natural log of W. Well, if W is 1, the natural log of that is 0. Doesn't matter what the constant is, your entropy is 0. Okay? So we do have a reference point here. Entropy, like enthalpy, is an extensive property. It depends on the amount of substance. And so you can't say that, the water has this much entropy without specifying how much water are you talking about. It's not like density. Density doesn't change with the amount of substance. That's an intensive property. The mass of a substance will change. If you double the amount, the mass changes. If you double the amount, the entropy is going to change. So it depends on the amount of substance. So a molar entropy is the amount of entropy for 1 mole. So here's a table from chapter 18 showing standard molar entropies for various gases, liquids, and solids. The units are joules per mole Kelvin because we're not talking about a difference here. We're talking about the entropy of this substance, and it depends on how much you have. So thinking about, room temperature, because 0 Kelvin's really hard to think about. Standard entropy of any substance is the amount of energy dispersed in 1 mole of that substance. And that's going to depend on the number of places that energy can be put, right? So the entropy of a substance is going to be affected by its physical state, its molar mass, the particular allotrope of the element you're looking at, molecular complexity, and extent of dissolution. So we'll look at all of those, of course. So the state of matter matters. So entropy of a gas is going to be larger than for a liquid. The entropy of a liquid is going to be larger than the entropy of a solid. Gases have more energetically equivalent ways to arrange their components. Liquids have more ways than solids do, right? So different numbers of places that the energy can be put. So if we look at liquid water, has a standard molar entropy of 70. Water in the gas state, 188. So a lot higher. Any questions? Molar mass is going to affect this. If we look at noble gases, helium down to xenon, they're getting larger. They're larger in physical size, also larger in mass. And if we compare their standard entropies, we see that the entropy increases with increasing molar mass. So how does that work? The energy states associated with the motion of heavy particles are closer together than the energy states for lighter particles. And so at a given amount of energy, you can disperse the energy in more combinations with the same overall energy. Does that make sense? It kind of made sense to me. This is a trend that only holds if everything's in the same state. So you got to compare solids to solids or gases to gases. So remember we had this we looked at so 2 particles, I think it was 4 joules. There's one level where the particles can be, they all have to be there, so that's a W of 1. There's only one possible combination here. If you have different levels, those aren't evenly spaced, but I'm going to make this 6 joules, and this 4 joules, and this can be 2 joules. 3 different levels, 2 particles. Now there's more ways that I can put the particles for them to have the same overall energy. Remember, the different states have to be energetically equivalent. I should have made one of these red. Now it's red. Okay. So I could put the red one here and the blue one there, right? That's 1. Or I could put the blue one up here and the red one down here. Does that have the same energy as this one? 2 particles, each 4 joules. Here's 2 particles, one's 6 joules, one's 2 joules. The total is the same, right? I could switch them. I could put the red one up high and the blue one down low. Now, if I have more levels that are close together to put those things in, can you see that there'd be more possible combinations that would be energetically equivalent? A larger particle is going to have its energy states closer together. And so there's more possibilities, and so it's going to have a larger entropy. Make sense? Allotropes. Allotropes are different forms of the same element. So one we're familiar with is allotropes of carbon. The most common ones are graphite and diamonds. So in a diamond, we have a three-dimensional array, covalently bonded together, very, very stable, very hard. Graphite is composed of layers, two-dimensional layers of carbon atoms bonded to each other, but held together between the layers only by intermolecular forces. And so that makes graphite slippery because the layers can slide. So these are two different forms of carbon. They are both pure carbon. They have different amounts of entropy. So the graphite is less constrained. These layers can slide relative to each other, and so it has a higher entropy than diamond. These atoms are stuck. They can't move relative to each other at all. So the diamond has lower entropy. The graphite has higher entropy. Does that make sense? Molecular complexity. So here we have argon and nitrogen monoxide. It's one of my favorite. I had to use that on my kids this morning. Gassed them with argon and nitrogen monoxide. Their molar masses are almost the same. And we want to keep that the same because we don't want molar mass differences to be an effect on the differences in the entropy. But if we look at the entropy, standard molar entropy, we see that nitrogen monoxide has a higher entropy than argon. So why is that? Well, both of these have translational motion, right? They're both moving through space. They both have rotational motion, revolving, spinning in place. But nitrogen monoxide also has vibrational motion where the atoms in the molecule can move away from each other and closer together. And so that's another place to put energy. Well, I guess the argon doesn't have rotational motion. Yeah, because it's like a sphere. It's symmetrical, right? So that's no different. Sorry. Screwed up on that one. Does that make sense, though? So the more ways that it can move, the more entropy it has. If we look at carbon monoxide and, ethylene, C2H4, again, very close to the same molar mass. The entropy is different. So the entropy of the C2H4 is larger. They're both molecules, but C2H4 is more complicated, right? You've got 2 carbons and 4 hydrogens, and so there's lots of different ways that the bonds could stretch and compress, right? If you get molar mass and complexity increasing, which is typically what happens unless you choose very carefully what you're comparing. So here, compounds of nitrogen and oxygen. As we increase the number of atoms, we're increasing the molar mass. We're also increasing the complexity, and so the entropy goes up. Any questions? Dissolving something. You dissolve a crystalline solid in a solution. The crystalline solid has a regular repeating 3-dimensional lattice of ions, right? It's very ordered. When you dissolve that, say in water, what happens to that order? It goes away, right? It becomes more disordered. So it makes sense the entropy increases. The energy that was concentrated in that crystal now is dispersed through the entire solution. So potassium chlorate as a solid versus potassium chlorate dissolved in water, the entropy is larger for the aqueous. We can calculate standard entropy changes for reactions. And this is similar to the way we calculated standard enthalpies of reaction. So you take the sum of the standard entropies for all of the products. And the standard entropies are in joules per mole Kelvin. So if you have more than 1 mole, you have to multiply it by the coefficient, and then the mole units will cancel out. So you use the coefficients from the balanced chemical equation, multiply by the molar entropy for all of the products, you add those up. And then you subtract the similar sum for all the reactants. So same idea as standard enthalpy change for a reaction. Important though, when we had standard enthalpies, anything that was an element in its standard state was just 0, and so we could leave it out. Standard entropies are always non-zero at 25 degrees. So you're not going to have elements that just drop out. You have to calculate everything. So here's an example. And to make things easier on all of us, I put up the needed values there for the standard entropies. So we're asked to calculate the standard entropy change for this balanced equation. So what we want to do is we want to take the standard entropies of the products, multiply them by their molar coefficients, and then subtract the sum of the products. The reactants. Subtract the sum of the reactants. So I have, and I'm going to be tedious and put the units in here. I have 2 moles of water, and the standard entropy of water entropy is 188.8. So 188.8, and that's joules per mole Kelvin. When I multiply those, the moles cancel out. And my other product is SO2. I've got 2 moles of that. So 2 moles of SO2 times its standard entropy, joules per mole Kelvin. And the moles cancel out. Okay, so those are my products. And I'm going to subtract the sum of the reactants. So 2 moles of the H2S. Each mole has an entropy of 205.8 joules per mole Kelvin. And 3 moles of oxygen, 205.2 joules per mole Kelvin. Moles cancel out. So 2 times 188.8 plus 2 times 248.2 minus the quantity 2 times 205.8 plus 3 times 205.2. So I'm getting negative 153.2 joules per Kelvin. Any questions? Like with so many things, a change is final minus initial. This is a state change. It doesn't matter how we got there. We just look at where we are and subtract where we started. So you take the standard entropies for all of these guys, and you subtract the standard entropies of the ones you started out with. Does this fit with the idea with gases that if you've got more particles, more moles of gases, you have higher entropy? How many moles of gases do I have in the reaction side? 5. And how many on the product side? 4. So that says that it's becoming more ordered. So the change in entropy is negative, and it is negative here. Is that always going to work? No. Because simple molecules have lower entropy than very complicated molecules, right? And so if the change in number doesn't match up with things changing in complexity as well, there are situations where it could possibly be different. Yes?
Can we have a complex example?
Can we have a complex example? You don't think this is...
They're easy and it's great to understand, but when you get to the homework and like the reviews and things like that, they're always so complex. I feel like I lose my mind.
For this example, honestly, I really can't think of a complicated example. I mean, it's just follow the pattern for this one. Yeah.